As a reminder, all waves carry energy. Sound waves carry energy. I'm projecting energy via my vocal cords. It's vibrating a small membrane on a microphone right now. That vibration sends an electrical signal to the computer, which records it. Then your computer plays it back, sends an electrical signal to the speakers, which causes the membrane to vibrate, sending that sound into your ears. Water waves carry energy. Earthquakes definitely carry energy, or the waves of an earthquake. Tsunamis, buildings topple over for earthquakes. There's energy in waves. And since light is an electromagnetic wave, light carries energy. Now, all of you have experienced this if you've ever gotten a sunburn, right? That the sun, which is 93 million miles away on average, 150 million kilometers, can burn you on a warm summer day, depending on your skin complexion and how long you're out in the sun. For a redhead such as myself, or former redhead such as myself, right? 15 minutes in the summer sun and I'm pink as a lobster. Those rays coming from the sun carry energy. That energy is deposited into your skin, causing burns. So, how much energy? Well, the intensity of sunlight, which is related to the energy. So the energy in a wave is proportional to the amplitude squared. The energy is also proportional to the intensity of the light. The intensity, or average intensity, of an electromagnetic wave depends upon the speed of light c, which is a constant, depends on the permittivity of free space, that epsilon naught, which is a constant, and then it depends on the maximum electric field strength squared. So E naught is the maximum electric field strength. Remember, the electric field is oscillating in an electromagnetic wave. How big those oscillations are determine the intensity of light. Now, this is if you know the electric field strength, the maximum electric field strength, the amplitude of that oscillation. But what if you know the magnetic field strength, right? Because light is an electromagnetic wave. We know that the electric field and the magnetic field are related by this relationship here. The electric field amplitude over the magnetic field amplitude is equal to the speed of light. And that the speed of light is 1 over mu naught times epsilon naught. So if we make this substitution, solve this for E and plug it in here, we find, I make the substitution, there will be 2c squared will pop up here. You saw the speed of light there. Take that c squared, so square this value. C squared is equal to 1 over mu naught over epsilon naught. Substitute that in. Epsilon naught will cancel. Mu naught will appear in the denominator. And then you'll have the intensity, or average intensity, as a function of the maximum magnetic field amplitude. The speed of light times that amplitude squared over 2 times mu naught, where mu naught is the permeability of free space, again a constant. If you want to know what the peak intensity is, it's just twice the average intensity. So whatever average intensity you calculate here, double it and you get the peak intensity. So that gives you an understanding of the intensity of light, how it varies given the square of the electric field strength. So light can be very intense or not terribly intense, following these relationships. And again, this is true for all electromagnetic radiation. Radio waves all the way up through gamma rays.